Hi everyone, in this video, we will show you how we achieve 6300 MB per sec file system performance to NVMe SSD on a Linux-based MP socket. In a typical Linux-based embedded system, NVMe performance is limited. Using PCIe Gen 3 hard IP and the standard Linux NVMe driver, file access is typically limited to around 1600 MB per sec due to software and architectural bottleneck. With 4 keys, our solution breaks through the 1600 MB per sec limitation and achieve up to 6300 MB per sec performance. This demo runs on Synopta ScalePad MP-SoC, specifically ZCU106 FPGA board. This demo is fully validated and complete system is available on our website. For independent verification in your own environment, when using a standard benchmark tool such as FIO, the write performance starts at around 4000 MB per second. That is already strong performance for a Linux-based embedded platform. However, we want to go further. Beyond standard benchmark, we develop our own performance optimized application called IO Erlang Perf. This application is designed specifically to maximize throughput using asynchronous I/O. With IO Erlang Perf, write performance on file access reaches up to 6300 MB per second. Here, you can see the performance improvement from a typical Linux-based embedded system to our Linux-based solution with IMNVMe IP using FIO and our custom application. To review the result in detail, we will demonstrate two applications side by side, FIO benchmark and our application IO Erlang Perf. The test environment includes ZCU106, Intel P5800 Enterprise SSD, and AB17 adapter board. Let's move into the live demo. First, we start with the raw box device performance. With FIO, the write throughput reaches around 4200 MB per second. But when using our IO Erlang Perf, the throughput increases to over 6300 MB per second. The difference comes from how the application submits and manages I/O. By reducing overhead and improving queue efficiency, we can extract much more bandwidth from the same system. Now we look at the read performance. With FIO, the read throughput is around 5100 MB per second. With IO Erlang Perf, the performance increases slightly to around 5300 MB per second. In this operation, the improvement is smaller compared to write performance. This indicates that the system is already close to the SSD practical read limit. Next, we move from raw box testing to a more practical scenario, file system testing. Here, the SSD is formatted with X10 and mounted under embedded Linux. This step reflects real deployment condition, where applications don't access raw box device directly, but operate through a file system layer. Now we perform the write test through the mouse file system. On the left, we run FIO, the standard benchmark tool. The result is approximately 4000 MB per sec. On the right, we run our performance optimized application IO Erlang Perf, and we achieve over 6300 MB per second. It shows that the performance gain isn't limited to raw box access. It is sustainable under real Linux file system usage. This demonstrates that our system can deliver NVMe Gen 4 throughput in practical embedded environment. So at this point, we have demonstrated write performance exceeding 6,300 MB per second on embedded Linux. That may raise an important question. How is this level of performance possible on an embedded platform? To achieve this level of performance, the entire system architecture must be optimized. Let's begin with the first key element, the Gen 4 SSD interface. The adaptive SoC doesn't provide a PCIe Gen 4 hard IP. To enable Gen 4 performance, we implement ARM NVMe IP with PCIe Soft Gen 4 from the side gateway. This provides a Gen 4 capable interface to the SSD. The interface is designed to fully support Gen 4 bandwidth at the hardware level. Second, hardware offloading. We use ARM NVMe IP together with a custom ARM NVMe block driver. Unlike the standard Linux NVMe driver, which handles much of the NVMe and PCIe stack in software, our architecture offloads the NVMe and PCIe processing into hardware. As a result, the software workload is significantly reduced. This minimizes CPU overhead and improves overall system efficiency. Third, dual-channel DMA. The Sync Ultra-Scale Path Processing System provides a 128-bit Xe4 interface running at 270 MHz. To maximize bandwidth, we use two Xe ports and we design a high-speed custom DMA engine that combines two 128-bit channels into a 256-bit array data path. This ensures proper alignment, data integrity, and high throughput. Fourth, high-performance application design. Even with optimized hardware and DMA, the application layer must also be efficient. Our application uses IO-Erlang. IO-Erlang provides shared memory submission and completion link buffer, and support asynchronous submission and completion. It also allows batch I/O submission, and it enables zero-copy data structure. This mechanism reduces system call overhead and context switching. The result is low CPU overhead and high throughput. This is how the application fully utilizes the performance enabled by the hardware. In summary, achieving 6,300 MB per second on embedded Linux requires end-to-end optimization. Gen 4 ready SSD interface, fully upload NVMe hardware architecture, high-speed dual-channel DMA, and a high-performance application built on IO-Erlang. Each layer contributes to performance. Together, they enable NVMe Gen 4 throughput on an embedded platform. Thank you for watching. If you want to learn more about our solution, feel free to reach out to us.